Hey, welcome everybody to Advent of Code 2022, day 10. So after the grueling ordeal that was day 9 for me, day 10, nice, it's a Saturday, and it was a nice gentle one for a Saturday morning. So that's good. I had a lot of fun doing this one. I think in general it was a pretty approachable problem. There was kind of just one gotcha that got me in the first part, that once I figured that bit out, then the solution came straight away. And then the second part, I was almost pretty much able to reuse all of the code, just add a little bit extra to it, and got the solution very quickly. I think it might have been on my first attempt that it actually just worked, which almost never happens to me. So that was a nice moment. Today is also the first example where the first section really sets you up for the second section. As in, if you do the first section, it's not that they change the problem slightly and you kind of reuse some code to try and solve the second question. It's that the second part is, so you solve a problem with your first section and then you use that as a tool to solve the second part, which is always a really cool way to do it. So you'll twig that as you go through the first part, what it actually asks you to compute might seem abstract, but it's actually because if you manage to get that computation right, then that allows you to do the second part, which I might be splitting hairs a little bit here, but I just think it is slightly different to how some of the other problems work, and I think that's really cool. I love when you see these kind of problems. So let's jump in. Day 10, cathode ray tube. We were previously crossing the river and on this dodgy rope bridge that we didn't think could hold our weight. Turns out it couldn't hold our weight, so we're plunging towards the river now, and we've landed in the river, and the elves are telling you, they're yelling at you that you're going to have to meet up with them another place. And you think, okay, this is perfect, I'm going to use my communication device. And you pull your communication device out, and it's got a big crack in the screen that water is pouring out of, and you now can't use it. So you determine that the screen is a cathode ray tube screen, which is like the old TVs, the old CRT TV screens. And it's controlled by like a really simple CPU, and it has a really simple clock circuit that runs on. So basically what you're trying to do is you're going to be trying to reproduce some like display logic is essentially what you're going to be doing. And you start off doing that with your input. So your input has pretty much just two commands. It's really basic. It has this no-op command, and it has another command called add x, which has a value associated with it, and you're told that there's a single register in the system, which is the x register, and this add command adds a number to that register. Now, this is where it gets a little bit confusing, and where I made my first mistake in solving this problem. So you're told that the no-op instruction basically takes one CPU cycle to complete. So you hit that instruction, it takes one CPU cycle, it doesn't actually do anything. So effectively the only thing it does is it just clocks one forward in a CPU cycle. You're then told that the add command takes two cycles to complete. Now, I kind of took that as being that, okay, well, when I execute it, it'll be two more commands time that I actually do the addition that it talked about, or that the addition that it was setting up would actually get executed. Turns out that's not quite how it works. So effectively I was assuming that the commands get executed basically in parallel. So you iterate through this list of commands, and that every time you hit an add command, you sort of like cache the value in a list, and then you get to the next command, and then you actually execute what that one was, because it took two cycles to execute. Turns out that's not what happens. If you kind of read this properly, you'd find out that effectively each command blocks. So when the add command gets executed, it sort of blocks, and it takes two cycles to complete, and then it performs the addition. So essentially this three command sequence actually takes 5 CPU cycles to complete. So the no-op command takes one cycle, this takes 2 cycles, and this takes 2 cycles. So by the time you're finished, you actually would be on the 6th CPU cycle, but you've only executed 3 commands. that was where I kind of fell down and mixed up my approach on the first part. But as soon as I twigged that, because my numbers just weren't adding up, as soon as I twigged that, then it made sense. So you're given this example command here. So it's a whole bunch of commands all in a row, and we're told that the computation that we have to do is a little bit weird. Basically, what we're told to do is start executing these commands, and you're keeping track of the cycles as you go. And then what you want to do is you want to find the value of the X register at 20 cycles, then again at 40 cycles, and then again at... So wait, sorry, what is it? I'm confusing myself now. Oh yeah, so it's 20 cycles, and then you're adding 40 cycles on to each time on from that. So you start at 20 cycles, then you go to 60 cycles, 100 cycles, 140, 180, 120. And at the end of that, so at each of those cycles, so at each point in your loop that you're going to have, when you've executed that many cycles, you're going to log what the value of the X register is at that point. And then the output that they want is basically a sum, it's the product of the cycle number and what the X register value is, and it's a sum across all of those. So it's a bit arbitrary, but it makes sense when you come to the second part. You'll see why that's very specifically what they've asked for to be the answer. So we need to write some code for this. I'll have a look here. It's not a lot of code. It's pretty short. I start off initializing a couple of values. The main thing here that we're keeping track of is we have a counter, and that counter is keeping track of my number of CPU cycles. Now, I wasn't certain exactly what way this is going to shake out, but it kind of makes sense to me to start this at 1, because we start off with the first cycle and then the second cycle. You could index it at 0. It's just in my head for some reason I decided to start it at 1. So there's a main loop that goes through. That loop is looping through the file and hitting each input as we go along. We do a check and we see if the count equals the output index. So in this case, I've initialized my output index with 20, which is the first one that we wanted to know the value at. If it does match that, I do the product that we talked about. I add it to this list of outputs, and I increment the output counter by 40. So that allows me to do my steps of 40 each time. So this is just the basic part of the loop that will execute for every single iteration, whether it's a no-op command or not. If it's a no-op command, then you're basically just doing this part. You don't have to do anything else, except you also increment the counter at the end once it exits. If it isn't a no-op command, so now it's an addition command, what I'm doing here, first of all, I increment the counter, because remember, we need to add an extra cycle in here. So whatever happens with this, it needs to add one more cycle. I add that cycle. And then I need to do the same check up here again, because every time you've incremented the counter, you're effectively in a new CPU cycle, and you need to check then if that CPU cycle matches our output index that we have. So we check that, then we do whatever that is, we log the value if it needs to be logged, then we update the X register value with the value that's in it. So this is effectively just adding a little delay loop in here. So not a loop, but essentially it's like, oh, wait, we've hit that add command. Let's wait for 2 cycles, and now we keep going. The position of when we increment this is very important, because it has to happen at the end of the cycle, and that's called out. That you start that addition cycle, it takes 2 cycles. Don't do your incrementing of your register value at the start. It actually does explicitly say it's at the end, and you'll get the wrong value then, because you'll have incremented it, and then your count could match the whatever 40, 60, 100 value, and then you'd be putting the wrong value in if you incremented it at the top. And that's basically it. So we do that loop for the entirety of all of our inputs, and then at the very end, we just collect together our outputs and we calculate their sum. And that is that. It's actually pretty simple and straightforward, not a lot of code. Logically, it's pretty simple once you realize what that delay means, that it's actually a little It's like a blocking command rather than the commands can execute in parallel. They just take 2 cycles to return, which is what my initial assumption was. So part 2. Now part 2 gets a bit crazy. Basically, we're describing how we want to draw a character to the screen. And it's a little bit abstract. You could read through this, but essentially what we're told is there is no vertical position. So you'd think if you wanted to draw on a grid display, you'd want to know the X and Y coordinate, and then you just color in that segment. This is actually an old style way of doing it, where you just have a single register that's just the length, the total length of all of the cells that exist, and you let them overflow to decide each one. So the numbers from 1 to 40 is the first row, and then it's from 41 to 80 is the second row, and so on and so forth. So by filling in the values along this one big long array, you pretty much build your 2-dimensional structure that we have to have the screen render stuff. So what we have to do now is, using the loop that we described, we're actually going to hook that in to the display and try and build the display logic. So it feels a little convoluted, but the numbers now are the key that we were told. So we have our index at 40, our index at 80, our index at 120, 160, 200, 240, which is quite similar to the sequence that we were asked up here. So this is what I meant by it sets you up really well in the first part to know that you're going to solve the second part. So if you reasonably can make sure that these are correct, then basically you're ensuring that you know that the second part should work with the same code, because you've already got the logic correct, and the sum, the multiplication and the sum tells you what the actual value is. So you know you've got that part correct, and then the second part will fall out then naturally from that. And you're basically using the first computation, the first part of that computation, as a tool to do the second part, which I think is quite cool. We're told that basically as you're going through this, you should know the index for each thing, for each character. You're told that at that point, if you get the register value that you calculated and you compare it to the index, if it's within 1 plus or minus of that, you're going to color that segment in your screen array. And then at the very end, it wants you to print all that out, and you should get a sequence of characters. So our test sequence looks like this, but what you should end up out with is a sequence of capital letters that you then type in as your answer. So I'll have a look at the code for this. And it's not much longer. It's a tiny bit longer. I've added my print command, which I reused from the previous day. Very handy just to be able to render the answer at the end. All this does is takes a 2D array. So you'll see up here, I set up my CRT, which is basically a 2-dimensional array of 6 rows and 40 columns, started colored in each one with a dot. Then what you have to do is you have to add the hashes into them to then spell out your letters. So it pretty much is the same kind of logic. We're doing the same logic. We have the same sets. We check a count compared against an output index. In this case, our output index starts at 40 instead of 20, and we're adding 40 each time, so that logic doesn't change. The only other thing I change in here is that basically once I've hit the output index, I know I've gotten to the end of this row, so then I actually just increment another index, which is for basically the vertical axis. So I just increment that by 1, which is the only real change there. Then in the not no-op loop, the only difference here then is that, so we do the same thing. We do our incrementing in the same way. We check if we're at the next overflow point onto the next line of the screen. The difference here is we fill in a value based on if the value of the register at that point is within plus or minus of the current index that we're at, if that makes sense. So we take the register value, we take a -1 and a +1 of it, and then we look at the actual index value that we're at, and we see are they within a range of each other. If they are, then we slap a little hash symbol in there. And that's it. So we do that here in this loop. We also do it down here in our other loop. These are essentially, this command is analogous to this command. So where we did them, we have to replace them with the other ones. So it's kind of like that anyway. So sort of where the logic lives. And yeah, we do our loop. We figure out what our array looks like, and then we get it printed out by our lovely print function down here. And yeah, they work pretty well. So the first one runs extremely fast, gives us our answer. And then the second part is a little bit slower, but it's still very, very fast. And it gives us a lovely answer here. There's our letters. The eagle-eyed among you may notice that this is actually wrong. The first character is off. And I noticed that when I was debugging this, when I ran it for the sample sequence, my first character was off. And I was like, oh, that's really annoying. And I was trying to debug why it was. And then I realized that the rest of the sequence was completely correct. And given that I knew it was going to be outputting a list of letters, I figured, if the first one's off, it's fine. Doesn't matter. I'll still be able to read what the letters are and solve the problem. So I did it. It's definitely just an indexing off by one thing, but it doesn't really make any difference here. So I didn't bother spending any time fixing it. And yeah, that is it for today. Not super hard, very satisfying though. I like these ones where you have some sort of tool basically that you build. The first part is a little tool that you build, then use in the second part to do something else, which I think is really, really fun. So yeah, hope you guys enjoyed that. And day 11 tomorrow. Let's bring it on. I'm hoping that they're gentle with us again because it's a weekend day, so maybe it won't be too bad. But the pattern seems to be one day's easy, one day's hard, one day's easy, one day's hard. Today was pretty easy, so I'm expecting tomorrow to be very hard. But yeah, we'll see what happens. Thanks for watching, guys, and I will see you all tomorrow. Bye-bye.